All right, so this video is going to analyze kind of a bunch of different stuff when it comes to graphs. Quick introduction, we're going to follow first here linear versus nonlinear. We're also going to get into discrete and continuous data, and then we're going to finish off with independent and dependent variables, all of which are really important when we are analyzing our graphs and understanding what kind of situation we're dealing with. In the grade 10 curriculum, you only deal with what's called a linear graph, which is a straight line graph. It deals with slope and things like that. And then once you move on from grade 10, you deal with a lot of other graphs that may or may not be linear. Things like quadratic graphs, cubic graphs, etc. So let's talk about how we can tell if something is linear or nonlinear. The first type of thing to look at is the graph. Now this is probably the easiest one to look at because all you're looking for is a straight line graph. So this is for sure a linear graph, so that's fine. A nonlinear graph is literally something that is not a straight line. So something like a quadratic graph, which is more of a grade 11 topic, this would not be a linear graph. It's still a graph, it's still got patterns and comparisons between x and y, but it is not linear. Second thing you're looking for is a table of values, or maybe just a general list of points that you're kind of comparing and contrasting. What you're looking for is an exact delta y over delta x comparison where it's the same all the way through your process, meaning that the change in y does not change as the change in x occurs as well. So in this example, we've got plus 3 for x for the first view, where it's changing by 3 every time, and then y is changing by 4 every time. So far so good. This would definitely be a linear comparison, right, where it's 4 over 3 and it's constant throughout. The jump here is that 12 goes to 18 and 19 goes to 27. However, if you think about what's happening here, this is a change of 6 and this is a change of 8. Well, really what's happening is we're missing 15 here and we're missing 23 there. So the table of values that's been provided to us kind of skipped out on some middle points, but it's still a change of 3, a change of 3, and a change of 4. So since the change is constant and it's 4 over 3, this is a linear situation. Nonlinear on this one, x is changing by plus 2 every time, so that's so far so good. And then y changes by 3, 3, and then 4. So it's 3 here, but then it's 4 there. That is not a constant change. It changed at one point while the other variable stayed the same. So that is not a linear relationship. And finally, the last thing that can tell you if something is linear or nonlinear is to look at their equations. What you're looking for is a degree of 1 in both of your variables. So for example, your y equals mx plus b situation that you may have looked at in grade 9, something like this, a random example, would be a linear graph. Something like d is equal to 3v plus 4. It's not y and x, but it's still a degree of 1, so we're okay. And then finally, maybe something like y is equal to x over 9. That's still okay because x is still a degree of 1. You could actually rewrite this as y is equal to 1/9 times x, and then it probably doesn't throw you off too much that that is a linear graph. So all of those being graphed out would be a straight line. Anything else that does not have a degree or highest exponent of 1, so something like y is equal to x squared plus 3, that is not a linear graph. Something like m times n plus 4 equals 7, not a linear graph because m and n is not a degree of 1. Even if you tried to get one of them by themselves, you'd be dividing them on the bottom, which is not a linear graph. So on that note, something like this is not a linear graph because this is actually a -1 exponent if it was over here. Let me just cross that out. It's actually equal to this, which is not a degree of 1. It's a degree of -1. So that is not a linear graph. Here we go. Discrete or continuous data along with independent and dependent variables. So if you want to pause the video and write this down, or if you just want to kind of watch it and listen to my explanation, feel free to do either one for yourself. So discrete data is discrete versus continuous is relatively straightforward. Discrete data basically just means that you have certain points on a graph or certain points in a situation that are not connected to each other in any sort of way. The best way to think about discrete data is there's no decimals between them. It doesn't mean that you can't have decimals. It just means, examples like, the amount of people versus something, or the amount of text messages versus something. Those are not things that you can connect the dots on, because then that would make the assumption that you can have half a person or a third of a text message or something along those lines. Whereas continuous data is things like temperature as it rises and falls throughout the day, and things that can actually have some decimals within them. So on the next page, and sorry, that's the graphical representation of that. But on the next page, I have some examples for you. So discrete data can only take certain values. So the number of students in a class, the results of rolling 2 dice, those are numbers and situations where you cannot have decimals. Whereas continuous data, a person's height as they get older, from baby to adult, you're going to have decimals within that. Time in a race, a dog's weight, the length of a leaf. All those types of things are all continuous data. So those can have all the decimals connected, whereas discrete, I don't connect them because often you don't want those numbers in between because they don't make sense. And then independent versus dependent variables. Independent variables are the variables for which we actually select the numbers. Often that's going to be on the x-axis pretty much every time. And then a dependent variable are the values that depend on what you've chosen. So if you've chosen something for x, you plug in some sort of calculation in the equation, and then the y value is produced, and that is the value that depended on what you did in the independent variable. So x is independent, y is dependent. Here's a great example of that. Frog jumping championship, and this is super realistic, obviously. George jumped a distance of 2 meters in a single leap. If George can maintain a distance of 2 meters on every jump, and the total distance traveled from the start is measured, let's figure out the relationship between the number of jumps and the total distance. Is this linear or nonlinear? Well, the number of jumps we have goes from no jumps to 1, 2, 3, 4, etc. And that means that he's now gone from 2 to 4 to 6 to 8, etc. That's going to be linear. The constant change in n, the constant change in d, is the same every time, so that is a linear relationship. Is it independent or deep, or which is independent, which one's dependent? It's independent the number of jumps. You can do as many jumps as you want, but the distance will depend on how many jumps you do, because George is maintaining that distance of 2 meters on every single jump, and we're calculating the total distance. So if George decides to do 5 jumps, he's going to get 10 meters of distance total. If he decides to do 30, he'll get 60 meters of jumps. He's just going to decide when he's done jumping. So number of jumps is independent. The distance he goes is dependent on that. There's your table of values for 5 jumps. Creating a graph, is it discrete or continuous? As you create that graph, maybe you've been following along with me so far, it has to be discrete because you can't take 1 1/3 jumps. The distance part could be decimal based, but the number of jumps you take cannot be half a jump, a third of a jump, a quarter of a jump. So this is a discrete data situation.